Let's start lecture 30 and the course is corrosion protection methods. So, if we have gone through this lectures till 29, we have talked about couple of aspects for corrosion protection like materials aspects, then design aspect, then environment aspect. Now, we will be talking about something which relates to the electrode. Now, whenever the corrosion is taking place, we talk about galvanic cell, and when we talk about galvanic cell, the material which corrodes, that will be anode in the system. And for the corrosion, we have 4 parts: anode, cathode, then electrode, then conductor and electrolyte. Now, once a material acts as anode, so the anodic reaction happens on that particular surface and continuous dissolution happens through the dissolution of ions from the surface, and electrons will be released to the anode, and those electrons will be used up by the cathodic reactions which will be taking place on the cathode side. So, now we have to do something to that anode so that the dissolution rate reduces to a great extent. Now, how do we do it? So, since we are talking about anode and cathode, that means we are talking about electrodes. So, one way to do it is by changing its potential. Now, when you change this potential, you can change this potential, that anode potential, to more negative side or to more positive side. So, that 2 ways you can change the potential. Now, in both the ways, you can have situations where you will see, as we discuss this particular aspect, that change in electrode potential and subsequent corrosion protection, that the material resistance to corrosion, or rather corrosion rate, reduces to a great extent, and resistance also improves to a great extent. So, when we do by changing this potential, then we have couple of aspects, couple of forms of corrosion protections like cathodic protection and then anodic protections. And in the cathodic protection, we have 2 variants: sacrificial anode, and then we have impressed current cathodic protection. And anodic protection, of course, you will see that it is applicable to a special situation, okay, and mainly to active passive metals. So, now let us start discussing this a new chapter, which is change in electrode potential and subsequent corrosion protection. Now, when we talk about corrosion protection by changing the electrode potential, as we have mentioned that it can be made to cathode or it can be made to anode by changing the potential to negative side. When we take the potential downwards, it becomes cathode. When we take the potential upward, then it goes into the anodic behavior, more anodic behavior. Now, if you see that there are, as we have mentioned, that there are 3 variations, rather 2 major variations in this particular corrosion protection route. So, one is cathodic protection, another one is anodic protection. And within this cathodic protection, in the cathodic protection, what we do? Try to make cathode. So, this metal we are trying to protect, and in the anodic protection, we try to make anode. So, here also this metal is to be protected. Now, under cathodic protection we have two segments. One is impressed current cathodic protection, which is in short called ICCP, and then another one is sacrificial anode. In this particular case, we actually make use of a DC power source and make the metal which is to be protected as cathode. And in this case, what we do, we make use of another active metal, more active than the metal which is to be protected, and connect them galvanically in that electrolyte. So, the active metal dissolves and the metal which is to be protected, that gets protected. So, here we use external DC power source. And here we use active metal galvanically connected. We can say galvanic coupling with the metal, and this is to be protected. Now, in this case, interestingly, we try to take the metal into the more anodic side or positive end in terms of potential. So, there we get to see that suddenly if we maintain that potential at certain level, we get to see a very, very low dissolution rate of the metal which is actually under protection. So, what we do? We make use of polarization, and that too anodic, and then anodic polarization, and this can only happen in case of active passive metal. Fine. And here also we use external power source, external DC power. Fine. Okay. So, now these are in brief some of the variations of protection of metals by changing the potential of the metal in that electrolyte. Now, if we try to understand the philosophy as well as the mechanics, or rather the mechanism how this protection happens, so we need to look into polarization part. Since we are saying that whenever the metal potential changes, that means we are actually incorporating polarization in the metal. So, we have to understand a little bit about polarization. So, in electrochemistry, polarization is very important since it actually talks about the electrode kinetics or the electrochemical reaction kinetics. So, that kinetics will guide us whether that metal will be protected cathodically or the metal will be protected anodically. Fine. So, let us look at the polarization. And this is in terms of electrochemistry. And when we talk about polarization, this is the effect, that when the potential changes, that is the effect, and the value, if we try to quantify polarization, that thing should come up in conjunction with this polarization, which is called overvoltage. And we mention it in terms of eta. Now, what is polarization? By simple definition, you can say the deviation of potential of electrode from its stable potential. So, this is, you can say, a definition. Now, there are a couple of things. Deviation of potential, that means change in potential. You can also mention it as change of potential, okay? And stable potential. We have to understand what is the stable potential also. Now, if we try to also see the potential of electrode, this is interesting term, potential of electrode. Now, when we try to understand the potential of the electrode, we actually talk about the reaction that is taking place on the electrode. Let us take example of a single redox process. We know that redox process happens on an electrode surface, What is redox? Reduction plus oxidation. So, from the reduction you take red and from oxidation you take ox. So, that becomes redox. For a complete electrochemical process, both oxidation and reduction must happen. Now, if we consider a simple example like Mn plus Ne equal to M. So, this is, if this way it goes, it is reduction, and if it goes this way, it is oxidation. And these happens on electrode surface. And that is what potential develops on that electrode surface. Now, when we try to look at a single redox process, that means there are no other reduction process, other reduction or oxidation process other than these species. That means Mn plus and M, there are no other species available. So, that time if you consider fixed temperature and pressure and you try to process that reaction in under closed system, okay, the system will try to reach equilibrium. So, this will try to reach equilibrium. With time, okay, and let us say this is closed system, right. And when it reaches equilibrium, then both rate of reduction and oxidation both are same, and reduction rate we consider in terms of IC, which is cathodic current density, and we know that current density is nothing but the rate of that particular reaction. So, since this is cathodic reaction and since it is involving electron flow, so then we can actually put a sign minus, and this minus sign is actually indicative of a negative current. Does not mean that the magnitude is negative, it means the direction. The direction of that current would be opposite to the line current, which is basically flowing from positive electrode to the negative electrode through the conductor. Okay. As per our electrical theory, current flows from positive terminal to the negative terminal through the conductor. Okay. So, this particular current flows opposite to that. For example, if current flows this way, this is positive terminal, this is negative terminal as per galvanic cell. So, let us, if it is considering, we consider galvanic cell where we are actually converting chemical or rather electrochemical energy to electrical energy. Fine. So, their positive terminal is cathode and negative terminal is anode. Fine. So, their current flows through the conductor from positive to negative. Now, when it flows, the electron flows this way. So, this electron flow can be assigned to a current flow which is nothing but IC, and since IC is flowing against the line current, so we are putting a negative sign. And when oxidation rate is considered, that time we consider it to be IA, anodic current density, and this reduction process is cathodic current density, because reduction is nothing but cathodic process and oxidation is anodic process. So, we can also mention like this is anodic and this is cathodic. Okay. Now, if we allow this system to reach equilibrium, if we fix temperature and pressure, and if it is a closed system and this species are Mn plus and M only. So, then at some point of time the rate of forward reaction and the rate of backward reaction both will be same, and that time we will achieve one condition which is called IC, and we are taking a mod value, just not taking negative value, equal to IA equal to I0, I naught rather. So, this is I0 is called exchange current density. Fine. And in IA is basically positive current, because this indicates this current, which is the line current. And why you are taking small I? It talks about current density, and we know that the rate is proportional to current density. If you go back, you will see, for example, if I try to find out the corrosion rate. So, the corrosion rate would be, if we know I core A is the atomic weight of that particular metal, N is that particular number of electrons associated with that reduction process, F is 1 Faraday, and if I try to put it in terms of millimeter per year, then there should be a rho term which is coming out. So, this rho is nothing but a density. So, rho is density, F is 1 Faraday, which is nothing but 96500 coulomb roughly, and A is atomic weight, and if you see corrosion rate in terms of millimeter per year, now A is, this is a constant term for a particular metal, this is constant for a metal, this is also a constant. Hence, corrosion rate is proportional to I core, which is nothing but current core divided by area of that metal surface where the reaction is taking place or the dissolution is taking place. Now, this exchange current density is basically the current density corresponding to the situation of equilibrium, and when it reaches equilibrium, it achieves a stable potential, and that stable potential can be measured with the help of standard potential, or let us say a standard electrode, let us say hydrogen electrode, standard hydrogen electrode we can make use of and then measure that stable potential. Now, if we leave that thing as like this, it will remain in that equilibrium position, but if we try to break that equilibrium, okay, so that breaking of equilibrium can only be possible if we have one of those reactions goes at a higher rate than the other. Okay. So, if let us say IC is greater than IA, then definitely the reduction is more. Reduction rate goes up compared to oxidation. So, then the system would not maintain its position at that equilibrium, it will break the equilibrium, and that time since IC is increasing, so we are actually sending more amount of electron. So, if IC has to increase, then this electron supply has to go up. So, if you are sending electron to a metal, so that means the metal negative potential is going up. or other way around, that if I try to see that stable potential, if we send more electron, that potential will drop. So, if we consider the stable potential to be E equilibrium, let us say E equilibrium, this E equilibrium would, that potential would drop. So, the new potential would be less than E equilibrium, okay. And then we say that the system is now polarizing. So, we can say this is polarization, fine. So, when polarization happens, we can measure the degree of polarization, that is measured with the help of overvoltage, which is nothing but E nu minus E equilibrium, and since this is less than E equilibrium, this would be negative, okay. And since it is happening because of more of cathodic reaction, we term it as neta C, okay. So, this overvoltage, cathodic overvoltage. So, this becomes cathodic overvoltage, fine. Now, similarly, if IA is greater than IC, okay. So, that time nu over potential would be greater than E equilibrium, okay. So, which is the stable potential when IC equal to IA equal to I0, okay. Now, that time I can also measure that polarization and this should be greater than 0, because this value is more than E equilibrium, and that time since it is happening because of the more of anodic reaction, we call it overvoltage, anodic overvoltage, fine. So, this is cathodic overvoltage, and this is and interestingly every time we are using this current in terms of current density. Why? Because we are seeing that the corrosion rate is proportional to the current density, or the reaction rate is proportional to the current density, not current. Why? Because this area can be different for a same metal in the same solution, okay, but the corrosion rate has to be same in the condition is same. So, then this area, because of the area change, we can have a different current, but the current density would be same, okay. So, that is what we are actually making use of this current density. Now, here we are getting two terms, which is overvoltage, anodic overvoltage and cathodic overvoltage, and that gives you the magnitude of polarization. And when polarization happens, actually we get to see that how cathodic protection happens, fine. So, now for example, if we talk about cathodic overvoltage, need to see it can be written in terms of so this is called Tafel equation, fine. This overvoltage can be quantified with the help of this is a Tafel slope, and this is exchange current density, this is the corrosion, this cathodic current density what is actually evolving due to the cathodic reaction, and this value is negative. So, this is negative and that negative term is incorporated here, that slope is negative, fine, and the beta c can be mentioned as let us see all those terms. R is gas constant, T is temperature, alpha is symmetry factor, we can assume it to be 0.5 considering that both the possibilities are same, whether cathodic reaction or anodic reactions. So, it has a serious implications on those cathodic and anodic reactions. So, let us not get into that, we assume it to be 0.5, and this has been explained in our earlier lecture series. Now, n is that number of electrons participating for reduction process, because we saw that m n plus n e equal to m. So, this is the n, and F is 1 Faraday, which is 96500 coulomb, okay, per 1 mole of electron. Okay. So, now if we have those things, then this beta c can be found out. Now, if we try to plot this, let us plot this. I can plot, let us see, over voltage, let us put over voltage with log I, and this I is current density. Now, since this is in the log scale, so I can actually will get to see a straight line, and somewhere we have I 0 in the according on this line. So, this is the equation, this particular very equation is plotted here. Similarly, the cathodic over voltage, anodic over voltage can be also plotted. And here I A is the anodic current, and this particular slope again I think you can put 1 minus alpha here, and here you can put alpha, and you can just reverse, you can also put here 1 minus alpha, does not matter. Only thing is that if this particular thing change, then there will be variation, otherwise not. Now, this is beta slope and this is positive, because whenever I am sending anodic current, then the potential is going up. You could see that as the current density, if I consider to be C, which is as we are increasing, the potential is dropping, potential is dropping. So, that is what this is cathodic over voltage. Now, if I try to look at this equation and if we try to plot it here over here in this particular graph, so that plot would be another straight line. So, here you could see, so this log I A, if we increase, the potential is going up, right, and they are crossing at some point, and this point is critical. This point, if you see, this particular line indicates IC, this particular line indicates IA, and at this point both IC is equal to IA, fine. So, that means it has to be I 0, which is exchange current density, and when that system is at equilibrium, our over voltage value is 0. Okay. So, that means at this point over voltage should be 0, which corresponds to E equilibrium, fine, and this is in volt. Over voltage is also termed in terms of volt, and this is in terms of ampere per centimeter square, let us say, fine. Now, if we do not have any external influence that which leads to a preferential reaction, like whether it is a cathodic reaction or anodic reaction. If it is cathodic reaction, definitely the potential will drop. If it is anodic reaction, definitely potential will go up. But if we do not do that, you will stay at this point, which is the equilibrium point. Now, let us say, let us see what happens. So, the IA is nothing but the anodic current, what it means? M minus Ne equal to Mn plus. So, that means it is basically indicating dissolution. So, higher the Ia, higher would be the dissolution rate or higher would be the corrosion rate, and at the same time lower the Ia, lower would be corrosion rate and lower would be the dissolution rate also. So, in fact, you will see that if we can take this Ia lower at a lower level, then we are actually incorporating a corrosion protection, fine. So, how can it happen? So, if we can, this is my equilibrium point, if we can take the potential downwards. So, let us say I take the potential at this location, and if we take it there, so what will be my IC? IC would be this, let us say prime, and what will be Ia? This is will be Ia prime, and this potential let us say E prime, and what is the position of this E prime? It is below E equilibrium. So, that means we have gone to a lower potential compared to E equilibrium. So, that means we are actually incorporating cathodic polarization. So, once we have cathodic polarization, we are actually increasing IC. So, that means we are sending more electron to the metal. Okay. So, more electron means this reaction, if it is equilibrium. So, the more electron means if I try to look at this way. So, that if we send more electron, so the reaction should proceed this way. So, when we proceed the reaction this way, what it means? I am consuming metal ion and then depositing as metal. So, which is not corrosion, which is rather protection. Okay. So, we are not allowing the metal ion to be stable there, it has to go back and then deposit on the metal surface. So, that is possible if we send electron, and whenever we send electron, we are taking the potential down. So, we are actually incorporating cathodic polarization. So, now when we do this cathodic polarization, we could see that the corrosion rate or the dissolution rate is decreasing. There is a finite amount of Ia definitely, but that amount would be so low that the dissolution rate can be negligible, and we can incorporate, we can term it as a protection. Okay. And that protection is possible if we do cathodic polarization. So, the cathodic protection is actually related to cathodic polarization, fine. So, now if I try to look at cathodic protection, so whatever discussion we had, we could see cathodic polarization, and the second term is sending electron to the metal. Okay. So, that way these two processes if we run, then definitely we can get a very low level of Ia or correspondingly very low level of dissolution rate. Now, if you see these two processes, cathodic polarization and sending electron to the metal, those are interconnected. If you send electron to the metal, it will go into cathodic polarization and it will lead to low Ia, lead to low dissolution rate, and it leads to protection. And this protection, since we are talking about cathodic polarization and protection, that is what it term it as cathodic protection, right. So, this is a simplistic way of understanding how to incorporate, how to understand, how to look into this this particular overvoltage versus log I plot and have a kind of idea about cathodic protection. Now, this is with reference to single electrode method. Okay, sorry, this is related to single electrochemical process or single redox process. But actual corrosion system is not a single reaction process, rather most simple process what we can think of is a two redox process, and this two redox process will happen, one of those processes will predominantly happen. For example, if we talk about zinc dissolution, then zinc dissolution would be the anodic process and hydrogen evolution would be the cathodic process. So, there actually we are not using the same species, rather we are using two different species. So, that situation we have to look at from this particular very concept, which is talking about cathodic polarization and taking the current density corresponding to anodic dissolution, whether we can take it down or bring it down. So, then we can incorporate cathodic protection. So, we will look at that part in our next lecture, but as of now what you understand that polarization, if you can bring in polarization for the dissolving metal, definitely you can have protection, provided you do cathodic protection. But let us see one small issue, that what happens if we take the potential up, because we have also talked about taking the potential up and then having protection. But here in this particular case it is not possible, because if we take the potential up, let us say you have taken the potential here. So, let us say this E prime double prime. So, this is corresponding to IA double prime, this is corresponding to IC double prime. Now, you see, had it been here in this particular, at this particular position, my dissolution rate would have been no dissolution, because equilibrium happens for the non-corroding system. Whatever metal is dissolving, that particular ions are again coming back and then depositing back on the metal surface. So, no corrosion system. But here what happens, if we go up, the IA is increasing. So, that means IA means correspondingly this reaction, and if that reaction increases, of course, my dissolution rate increases. So, I cannot remain at that position of equilibrium, I am away from equilibrium, and this is anodic polarization. It does not lead to any benefit, rather it increases the corrosion rate. But we will see later that for active passive metal, as we keep going up in the anodic potential range, at some point of time we will achieve passivity, and there we can have a very interesting phenomena, and that phenomena leads to one particular protection, which is called anodic protection. We will talk about that. But next class we will talk on this particular behavior, which is the actual corrosion process, and this is single reduction process or single redox process, but there we will be using actual corrosion process, where we will be taking two different species, two different redox reactions, and that will be interesting. That time we have to see whether the cathodic polarization can lead to a decrease in anodic current density, and subsequently we can have corrosion protection. So, till then, thank you.